Okay, so here's again, here's our electron double slit experiment, or a quantum particle double slit experiment. Um, and a couple key points here, and that is that the detector, what we would find if we were to do such an experiment. Okay, so I should point out that um, as we'll learn in the next few lectures, in order to actually do an experiment as I've shown here, you would have to be able to fabricate this double slit apparatus to such small dimensions that it's very, very difficult to do, and actually only became possible in the last 10 years or so. But if we were able to make if we can envision such an experiment, and now it's been done, where the electrons essentially all have the same energy, we have this geometry, then what we would find, actually what people have found, is that the detector would basically just register a click every time that an electron, a particle, was detected. And what we find is that the rate of the clicks varies in proportion to the probability of detecting a click. So if we move this detector to different positions, the rate at which the clicks happen, click, 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 varies depending on where the detector is. But the volume or the sound of each click is always the same. We never get very light clicks and then very heavy clicks. We always get the same volume, if you will, of clicks. And there are no half clicks, okay? So every click seems the same. And also, if we were to use two detectors, okay, somehow, putting two detectors here, no matter where we put them with respect to each other, they would never click simultaneously, as long as we ensured that that the electron gun was such that it didn't put out two particles, two electrons at the same time. So under those circumstances, we would never detect two clicks at the same time. We would never register two clicks at the same time if we were to use two detectors. And basically what all these points suggest is that the energy in this experiment is concentrated in packets, and so it's quantized. And this makes sense to us because we usually think of electrons as particles. So we would expect, just like with bullets, that since they're particles, that we would get this kind of behavior where we would detect individual clicks, that all the clicks would be the same, and that we would never be able to detect two clicks simultaneously if we were to use two detectors, because it can only hit one detector or the other, any given electron. Okay, so if we were to cover one slit at a time, then we would get these probability distributions that are very much like the ones that we saw for both waves and normal particles, bullets. If you close this slit, then you would get this probability distribution P1. If you were to close the other slit, okay, then you'd get this probability distribution P2. And since we have individual particles, since we know that we have quantization of the energy, so we have individual quanta, these electrons are quantized, then what we would expect, maybe if we think about the bullet experiment, is that when you open up both slits, that you'd get just something which looks like one peak in the middle. But lo and behold, if you actually do the experiment and you do it right, which is difficult, very carefully, what you find is that you get interference, just like we saw with the waves. Okay? And so even though it's clear that we're detecting individual electrons, that individual electrons are what's going from the electron gun to the detector, okay, we still see interference that looks very much like the interference from a wave. Okay? And in fact, if we again look at the probability distribution, if we look at the shape of this, we can work out the math, and again it's equal to the sum of two amplitudes, phi1 plus phi2 squared, which again, if you expand it, gives you the same kind of thing, interference term, where you have a phase difference between the two amplitudes.